So here we're going to talk about using information about the concentration of a chemical or pollutant in the air and water to figure out whether a chemical is going to leave the water or go into the water. So this is movement between air and water. So you'll recall Henry's law constant. We've already spent quite a bit of time with this constant as being, and here we're going to be using mostly the unitless version, as being the concentration of a chemical or pollutant in air over the concentration of a chemical or pollutant in water. And this is generally considered to be at equilibrium. And here we're going to use this idea to predict where chemicals in the water will go, whether they will go into the air or into the water. So will they transfer into the water or will they transfer out of the water? Okay, so the basic idea is that for any measurement, actual measurement of a chemical in the air, so the concentration of a chemical in the air, there will be an equilibrium concentration in water. And we can call that C, water at equilibrium, or we can just abbreviate it as CEQ. Okay, so to use this idea, we're just going to rearrange this equation. So this is the basic Henry's law equation, but now we're using the measured amount in the air to estimate the amount in the water at equilibrium based on this concentration. So we just rearrange this equation, and here I'm using the CEQ instead of C of water at equilibrium. And we estimate that using the concentration of the chemical in the air and the unitless Henry's law constant. Okay, so what does this do for us? So then we compare the actual measured amount of a chemical in water to this CEQ to predict how things are going to change. Is that chemical going to move into the air, or is the chemical going to move into the water? Okay, so the flux of that chemical is going to depend on the difference between the actual measured concentration in the water and the estimated concentration that should be in the water at equilibrium. So if the amount that's in the water that you measured is greater than the amount that should be there at equilibrium, which again we estimated with the actual measured amount in the air, would you expect that the flux would be to the water or to the atmosphere? So out of the atmosphere into the water, or out of the water into the atmosphere? So you can think about that for a moment. And the idea is that if there's more chemical in the water than there should be at equilibrium, you would expect for that chemical to go into the atmosphere, so from the water into the atmosphere. So on the other side of that idea is that if the amount that you measured in the water is much less than the amount that should be there if you're at equilibrium, so would the flux then be to the water or to the atmosphere? You can pause for a moment, think about that. And then you need more in the water, so you're going to have a flux to the water from the atmosphere. Okay, so that's the basic idea behind this sort of estimating or predicting where the flux is going to be, to the air or to the water. Okay, and we use that idea then to make this general equation for air-water exchange. So where J, again, we're calling it the flux density. It's in mass per area per time. We've got the concentration, the measured concentration in the water. And then here is our estimated, what it should be, the concentration of the chemical should be at equilibrium, which we're estimating by the measured amount in the air over the unitless Henry's law constant. Okay, so Kw is something new. You haven't seen that before. That is the gas exchange coefficient for the chemical of interest. So if you're talking about propane, this would be all the concentrations of propane in water and air, Henry's law constant for propane, and then the Kw for propane. Okay, so just to take this concept a little bit further, think about whether J should be positive or negative, depending on if you have the flux from the atmosphere or to the water, or from the water to the atmosphere. You notice that Kw here is negative. So if you have the C, the concentration of the chemical in water at equilibrium, if that is greater than the amount that you measured in the water, is J going to be positive or negative? So you can think about that for a moment. So J in that case is going to be positive because this number will be negative, and you're multiplying these two, so you end up with a positive number. And then that means that you're going to have flux from the atmosphere into the water. Okay, the opposite situation, so you can already probably answer this question, is when you have the concentration in water which is greater than the amount that should be there at equilibrium. So in that case, you're going to have a positive number here multiplied by a negative, so your J is going to be negative. So a negative J means that you've got flux to the atmosphere from the water. Okay, so we've got this equation now, and how do we get KW? KW is not something that we always know. Sometimes there is a table that will show you KW of some gases or pollutants, but not all of them. So we can estimate KW, and we can do that using what we know about molecular weight and the fact that KW increases with molecular weight, and a known KW and molecular weight. So we can use the molecular weight of a chemical that has a known KW to estimate an unknown KW, because we always know the molecular weight of the unknown substance, or the substance with the unknown KW. Okay, so we just use sort of a cross-multiplying idea where we have the KW of the unknown and the known, and then we have the molecular weight of the known over the molecular weight of the unknown, and rearrange that equation to solve for the KW of the unknown. Okay, so here's an example that I'm going to go over in a separate short video, just to let you know that that is coming. Okay, so what you can do now after watching this video and the example is estimate the flux of chemicals dissolved in water to the atmosphere. And in class, we'll talk about estimating the flux of chemicals to the atmosphere in non-aqueous slicks. So this would be like an oil slick or some very non-polar substance. And that's it for now. Thanks for watching.